distinguishing between the mother raised her children versus the mother raised her children.
Okay, phonetically, those are very, very close.
They're incredibly close. The difference is minimal. It's about whether a consonant cluster is voiced or voiceless, but grammatically.
Both raised and raced fit perfectly in that sentence. They're both plausible verbs.
Which means if the listener doesn't catch that tiny phonetic difference, that little bit of voicing, they'll probably default to the most common, socially expected phrase.
The mother raised her children.
Of course. But in this specific dictation, the correct written answer was raced. So the phonetic imprecision, even a tiny bit, forces the listener into this high-stakes 50-50 guessing game where the wrong guess means a total loss of meaning.
And the insight there for you, the learner, is just crucial. Relying on context is a strategy, yes, but it becomes a really high-risk one if your phonetics aren't clear, especially with words that sound similar.
Yes, and the material really stresses this. The need for phonetic precision goes way up when words are presented out of context.
Like in a dictation.
Exactly. Students often panic with simple dictations of single words like pen, pin, pain, or pan, or 10, ton, tongue, and tone.
Because there are no clues.
There are no clues. They're used to the sentence clarifying the meaning. When the word is stripped bare like that, all those subtle differences in vowels and final consonants, they suddenly become the only markers of meaning. And that's exactly where the guessing strategies fail.
So moving beyond the pure mechanics of clarity, the sources also touch on a much deeper, more social level, accents and power dynamics. This seems less technical, but maybe even more influential.
Oh, it's deeply social. The observations that basically prestige determines tolerance.
Okay, what do you mean by that?
If a language or a culture has high prestige, the sources use French as an example because of its historical influence, then a French accent, even if it's not perfect, is often seen as charming or cute or sophisticated.
It gets a social pass.
It gets a social pass. The accent itself takes on the perceived value of the culture it comes from.
But if the culture doesn't have that prestige,
then the exact same phonetic deviations are just perceived as hard to understand. Or worse, they get associated with a lack of education or sophistication.
there's that anecdote about the Texas broadcaster.
Yes, that's a really poignant one. He was a radio personality who consciously decided he had to change his thick, rural Texas dialect when he moved to a major national market.
And why did he feel he had to do that?
He admitted he changed it because, as he put it, having lots of listeners tell you every single day that you're really stupid just because of how you talk, it becomes emotionally and professionally debilitating.
It wasn't about the content of what he was saying.
Not at all. It was just his pronunciation patterns. They marked him as other. The sources make a tough point here. These are reactions we can't always control, even if we choose not to say them out loud. We are constantly judging a speaker's perceived intelligence through the filter of their accent.
That's a harsh reality, but a realistic one. It puts the burden on the speaker who wants to maximize their competitiveness. Does the source material offer, I don't know, any counter-arguments here? Or is it all on the speaker?
It frames it as empowerment. The key takeaway is not that you have to completely get rid of your accent. The goal is that your accent must be understandable.
So clarity is king.
Clarity is king. And if your accent happens to carry some potential social baggage that might imply you're less intelligent or sophisticated in a formal setting, the material suggests you need to be prepared to adopt a more standard variety, like general Americans.
The ultimate goal is always clarity. Reduce that listener's cognitive friction.
Always. And the final piece of advice in this section really ties back to the learning process itself. It's about seeing these mistakes not as flaws, but as something else.
As opportunities.
Yes. The text encourages you to view phonetic issues, a mispronounced vowel, a misplaced stress, as gifts. They're opportunities to notice things you never noticed before, to gain a new sensitivity to the language.
So if you struggled with raised and raced,
that's a gift telling you exactly where your ear needs more training.
That sets the stage perfectly. So communication has this social cost if we ignore articulation. If we want to fix the problem and move to clear, comfortable speech, we have to understand the machine itself. So let's move to lesson 2, the physical engine of speech.
Exactly. When we talk about phonetics, we're really talking about engineering the air. The core principle here is that speech is all about articulation and acoustics. We're dealing with measurable physical things: pressure, vibration, resonance.
Let's start with some definitions just to ground us. We know phonetics is the study of sound, but what is articulation in this specific context?
Articulation is, technically, the movement of parts held together by a movable joint. For speech, it's all about the incredibly precise movements of the organs in our vocal tract.
So the tongue, the lips, the jaw.
Primarily those, yes. And it's so important to remember that the tongue isn't just some passive flap of muscle.
Right.
The material emphasizes that the tongue is arguably the most flexible and precise organ in the entire body. In terms of fine muscular movement, it's a superstar. It performs this incredibly complex, rapid choreography that defines almost every sound we make.
But none of those gestures, none of that choreography works without a power source. Where does all that energy come from?
It all starts with the breath, specifically breathing out. The basic source of power is the respiratory system. It acts like a bellows, pushing air out of the lungs.
So it's just wind power.
It's pure wind power, regulated by the diaphragm and the rib cage. This air travels up the windpipe, the trachea, and into the larynx.
We really take for granted that we talk while breathing out. Why is it so hard to speak when you're breathing in?
Well, we speak on the outward breath because it provides a consistent, controllable stream of air pressure. When you try to speak while breathing in, the airflow is unstable, it's choppy, the vocal folds are fighting against an inward pull instead of an outward push.
The source material actually says to try it.
Yes, and if you do, you can manage a few sort of distorted, gasped words. It sounds like something out of a horror movie, as the source puts it.
Why does it sound so strange?
Because the normal, stable flow of air and the natural rhythm of the vocal folds are totally disrupted. It's physically inefficient. You just can't sustain it.
Okay, so the air, powered by the lungs, arrives at the larynx, the voice box. This is where the first huge distinction between sounds happens. Voicing.
Yes, the larynx houses the vocal folds. Phoneticians prefer folds over chords because they're muscular flaps, not strings.
Two small muscular flaps.
Two small muscular folds of tissue sitting horizontally across the top of the windpipe. And how they're positioned determines if a sound is voiced or voiceless.
Let's break down those two outcomes. We can start with voiceless sounds.
For voiceless sounds, the vocal folds are held apart. This creates a wide opening. It's called a glottis, and it allows the air a relatively free passage into the mouth.
So no vibration.
Since the air just flows through without making the folds touch, there's no vibration. Think of sounds like F, S, P, or T, just air.
Okay. Now for the voiced sounds. This is where the physics really kicks in.
This is the critical mechanism. For voiced sounds, the folds are adjusted so they're very close together. The airstream rushes past them, which creates a drop in pressure.
Which sucks them together.
It sucks them together, only for the air pressure building up from the lungs to force them open again. And that cycle repeats incredibly rapidly.
How rapidly are we talking?
For a typical male speaking voice, they vibrate at around 100 to 120 cycles per second. That's hertz. For a typical female voice, it's often closer to 200 hertz. And for a high soprano, much, much higher. That rapid, continuous vibration is what we mean when we say a sound is voiced.
So what controls the pitch? Why is one voice 100 hertz and another 200 hertz?
It's all about the tension and the mass of the folds, just like a guitar string. Thicker, less tense folds, typically male vibrate slower, which gives you a lower pitch.
And thinner, higher tension folds.
Typically female vibrate faster, resulting in a higher pitch. The difference is purely physical. It's a manipulation of tissue mass and tension happening in milliseconds.
That instruction from the source for the listener is great here, to feel the physics in real time.
Yes. If you put two fingers lightly on the front of your throat, on your Adam's apple, and you make a long, sustained, voiceless sound like zzz, you should feel nothing but air.
Right. Nothing.
Now switch immediately to its voice counterpart. Zzz. You should feel a really distinct, unmistakable buzzing or vibration.
Oh, yeah, you can definitely feel that.
That buzzing is your vocal folds slamming open and shut 200 times a second. Training your ear and your throat to feel that physical difference is fundamental for English, especially for pairs like P and B, T and D, K and G.
What's really mind-boggling is just the complexity of coordinating all of this. The pitch changes, the volume, switching from voice to voiceless. It happens hundreds of times a minute.
It's an incredible feat of unconscious control. The material makes a great point, that if our conscious brain had to control all those movements, adjusting the folds, regulating the air, moving the tongue,
speech would be a mess.
A total mess. We'd stutter, we'd stop, we'd be incapable of speaking at a normal speed. All of this rapid, precise coordination is managed by the brain's motor cortex, completely below our level of awareness.
Well, once the sound gets past the larynx, it enters the vocal tract. This is the main shaping space. This is where the gestures of articulation happen. So let's talk about the specific tools, the articulatory organs.
We can do a quick tour from front to back, looking at their function. These are the fixed points and the movable parts we use to create all the constrictions and closures that define our sounds.
Okay, starting right at the front.
We have the lips, upper and lower. They're used for what we call bilabial sounds, like B, P, and M. Simple closures. Then, just behind your upper teeth, you can feel that little bony bump.
The alveolar ridge.
The alveolar ridge. And this ridge is absolutely essential for English pronunciation.
Why is it so crucial?
Because so many English sounds are made there. Your T, D, S, Z, and N.
Mm-hmm.
The tongue tip, or blade, touches or gets very close to that ridge. In many other languages, the T and D are made further back, maybe against the teeth. That subtle difference in placement is an immediate cue to a native listener. Mastering that spot is a huge step.
Then we have the star of the show, the tongue. You said we need to think about its different parts.
That's right. We divide it for description. There's the tip, the very end. The blade, just behind the tip, which makes contact with that alveolar ridge. Then the front, the back, and the root, which is the lowest part. Every single sound involves a specific gesture from one or more of these sections.
And the roof of the mouth is the upper boundary.
That's divided into the hard palate, the bony front part of the roof. And that transitions into the soft palate, or the velum, which is the muscular back part. It's very flexible, and ends in that little hang-in thing, the uvula.
And the soft palate is the key for nasal sounds, right?
Absolutely critical.
Yeah.
When the soft palate is raised, it presses against the back wall of your throat and closes off the path to your nasal cavity. Air has to go out through the mouth. That's how we make oral sounds, like all our vowels, T, T, A-S.
But when it's lowered?
When it's lowered, that nasal passageway opens up. Air escapes through the nose. And that's how we get nasal sounds like MN and the English ing sound. If a learner doesn't raise it enough, all their sounds can get an unwanted nasal quality.
And the final piece, the last safety mechanism in the system.
That's the epiglottis. It's that small flap that acts like a protective lid. Its only job is to close over the windpipe when we swallow so we don't choke. It's not involved in making sounds, but it's essential. It stays open when we're breathing or talking, letting the air pass up to the larynx.
This review just makes it so clear. Phonetics is applied biology, and physics, every sound is a physical event. And understanding that physical reality moves us perfectly into our final and maybe the most overlooked lesson, how all these physical sounds are organized into the rhythm of English.
Exactly. If the first two lessons were about the social need and the physical hardware, lesson 3 is all about the software and the timing, mastering the subtle rules of English intonation and stress. That's what truly separates comfortable, native-like speech from speech that sounds, awkward and incorrect.
Even if all the individual sounds are perfect.
Even then.
Let's start with a really foundational rule that a lot of non-native speakers miss. The rule of compound stress. This seems to have a huge impact.
It's a critical structural rule for compound nouns.
Right.
So words that are made by sticking two nouns together to make a new concept, like noun plus noun. The rule is very strict. The main stress must fall on the first element, not the second.
And that stress pattern signals to the listener that it's one single thing.
Immediately. It tells the listener that the two words function as a single unit.
Can you give us some examples of how the meaning changes with the stress?
Sure. If you say a blackboard with stress on black, you're talking about the thing in a classroom, the compound noun. But if you say a blackboard, stressing board, you're just describing a board that happens to be black.
Okay. A hot dog versus a hot dog.
Exactly. A hot dog is the food. A hot dog is an overheated canine. Or a greenhouse where you grow plants versus a greenhouse, which is just a house painted green.
So, using our own material here, we would talk about phonetics resources, speech production, vocal track,
and airstream mechanisms. Stressing that first element binds the two words together in the listener's mind.
And if a learner gets it wrong?
If they stress the second element, like phonetics resources, the listener hears it as if the speaker's being very excited or something, but ultimately it just sounds awkward and incorrect. The sources compare it to a tonal error in a language like Mandarin.
Like saying han hao with the wrong tone?
Exactly. It's not just a pronunciation mistake. It's a structural error that clouds the meaning.
So rhythm isn't just for decoration. It's fundamental to the grammar.
Absolutely. The listener needs that auditory cue to process the words efficiently. If you get the compound stress wrong, you make them stop and rethink what you meant.
Okay, next, let's talk about how we translate writing punctuation into sound, the hidden language of intonation.
This involves two major things working together, the continuation rise and tonic stress. These are the rules for how we read complex sentences out loud.
Let's start with the continuation rise. That's the little song that tells you a thought isn't finished.
Right. When an idea is unfinished, like at a comma or in a list, your voice has to use a rising intonation. You sort of hang the pitch up high to signal, wait, don't assume I'm done, there's more coming.
And if you use a falling tone there,
The listener thinks the thought is over.
Mhm.
And then they get confused when you keep talking and add more information.
So if I were reading a long sentence like, the components of speech, including the larynx, the tongue, and the soft palate, all work in concert.
Your voice would have to rise on larynx, high pitch, rise again on tongue, and rise on soft palate before you finally drop your pitch on concert to signal the end. That rising pattern is mandatory in formal reading.
And this ties right into the idea of tonic stress.
Tonic stress is the peak of that pattern. It's the rule that the final stressed word, the last important content word in any phrase or thought group, has to be produced on the highest pitch.
So in a list,
If I say, she bought a book, a new dress, and a beautiful blue hat tee, the word hat gets the highest pitch and the most emphasis. It marks the end of the list. If you don't make that final stress high enough, the speech just sounds flat and robotic.
and speaking of formal speech, the material had a really specific point about the final ing sound.
Yes. This is a subtle but important marker of formality. When you're reading, formally giving a speech, presenting research, you have to make sure you use the full pronunciation of the final ing as a ing.
So using the N sound at the back of the mouth.
Exactly, the velar nasal.
Yeah.
You have to consciously avoid the more relaxed, casual pronunciation tone, which just uses an N sound. Using that shortened tone when you're reading formally can sound unprofessional, even though we use it all the time in casual chat.
That level of detail shows how deep rhythm goes, which brings us to maybe the most fundamental part of English flow, the importance of stress timing.
This is probably the single biggest mechanical difference between English and so many other languages. English is a stress-timed language.
Okay, what does that mean in practice?
It means the amount of time between one stressed syllable and the next stressed syllable is supposed to be roughly equal. It doesn't matter how many little unstressed syllables are squashed in between them.
And that's different from, say, Spanish or Mandarin.
Yes, those are generally considered syllable time languages. Every syllable gets roughly the same amount of time.
Yeah.
In English, we throw that rule out. The stressed syllables are long and strong, and the unstressed syllables have to be radically shortened and compressed.
The sources say they die between the stressed syllables.
It's a vivid way to put it, but it's true. They have to get crushed to maintain the rhythm.
And this compression all depends on reducing the vowels.
Absolutely. This is the secret to English rhythm. The reduction of unstressed vowels to that neutral, muffled vowel sound we call the schwa, the U sound, like the first vowel in about or away.
So we don't say, I went to the store with equal weight.
Never. We reduce the little function words to and a wit, though they almost disappear. It sounds more like, I went to the store.
So the big content words, nouns, verbs, adjectives get the time and stress, but the little grammar words, prepositions, articles get ruthlessly compressed.
They get compressed into the schwa. If a learner pronounces every single syllable with equal clarity and time, it just immediately shatters the English rhythm. It sounds robotic.
The challenge then is training your ear to even hear that reduction, let alone produce it.
It's very hard. Like in the sentence, I can go, the word can often reduces to kun with a schwa. It's very hard to catch if you're listening for the full, clear vowel sound.
Now, even with the stress time system, there's another adjustment we have to make when the content gets really dense. The rule of rhythmic pausing.
Yes, this is what you have to do when you get a string of single-syllable content words all in a row. These are words with heavy meaning, so you can't really reduce them.
And if you rush through them.
The density of information just sounds unnaturally fast and choppy. It overwhelms the listener.
The example of the anatomical description from the source is perfect here.
If we go back to that description from lesson 2, 2 small muscular folds. If you try to say 2 small muscular folds is one big word, it's just jarring.
It's too much.
The correct natural English rhythm requires tiny, almost imperceptible pauses to give the listener's brain time to process. 2 pause, small pause, muscular folds. Those little pauses are essential for clarity and cadence. If you skip them, you lose the flow, and you're right back in that tired listener zone.
Finally, we circle back to the sounds themselves, but with a focus on listening for subtlety, especially in those common trouble spots.
Vowel distinctions are a huge one, especially vowels that exist in English, but maybe not in the learner's native language. The sources point out areas of confusion, like the difference between ton, tongue, and tone.
All very different words.
Very different, but phonetically close. Or the distinction between sour and sour. These words might translate to similar concepts in another language, but in English, they are distinct sounds and have to be mastered to avoid confusion.
And the other big challenge is with final consonants, specifically the idea of unreleased stops.
This is so often the reason dictations are hard. Final stop consonants like T, P, or K are very often unreleased in English. This means you make the mouth gesture, your tongue goes to the alveolar ridge for a T, your lips close for a P, but you don't release that puff of air.
The source called it Mayu Tuzu, no air puff.
Exactly. The sound is cut off before the puff.
So if there's no puff of air, how is a listener supposed to even know the consonant is there?
It's incredibly difficult, especially out of context. This is why a dictation of bat versus bad can be so hard. When that final consonant is unreleased, the main clue that tells you which word it is isn't the consonant sound itself. It's the effect that consonant had on the vowel right before it.
You mean the length of the vowel?
Precisely. In English, vowels tend to be a little bit longer before a voiced final consonant, like the D in bad. And they're a little bit shorter before a voiceless final consonant, like the T in bad.
So you have to train your ear to hear vowel duration, not just the consonant.
You have to listen for those tiny subtle differences. That slight voicing difference is critical for clarity.
This has been such a comprehensive look. It really shows that phonetics is not some abstract theory. It's an immediate, practical application of biology, physics, and even social dynamics.
Absolutely. And to recap our three big lessons. First, clarity is a social necessity. It's about maximizing listener comfort and making your communication more effective, more competitive. Second, articulation is a physical reality. It's powered by controlled breath and shaped by the incredibly precise, unconscious movements of your tongue and vocal folds.
And third?
And third, mastering English rhythm driven by stress timing and those hidden rules of compound stress is absolutely essential for achieving a natural, intelligible flow.
So the final takeaway for you, the learner, what's the ultimate goal of diving this deep into the science of sound?
The goal isn't just about correcting faults. It's much bigger than that. It's fundamentally about developing a keener sensitivity to sounds and to language in general.
Keener sensitivity.
When you start to see every mistake, like we said, as a gift, as a chance to notice something you never saw before, you gain this fundamental skill for understanding how language really works under the hood. You start hearing the speech reductions in movies, the tiny differences in regional accents, the little pitch changes that signal a joke. It completely changes how you listen to the world.
That reframing from just correction to sensitivity training is brilliant. To end this deep dive, let's leave our learner with a provocative thought, something that builds on all that physical complexity we talked about in Lesson 2.
Okay. Take a moment and just consider the human tongue. It is one of the fastest and most precise organs we have. It's capable of millisecond adjustments in its shape, its tension, its position. Now think about the sheer amount of work your unconscious brain is handling every time you say one simple sentence.
The milliseconds of movement.
The milliseconds of finely coordinated muscular movements, the 200 hertz vibrations of your vocal folds, the air being redirected through your nasal cavity, the continuous adjustments in pitch and volume, all happening perfectly without you ever consciously thinking about it. The vocal tract and the brain that controls it is probably the most incredible high-precision machine you will ever operate.